Today we will start chapter number 12, current electricity, and we will study electric current, conventional current, drift velocity in conductor, electroencephalogram, EEG, Ohm's law, and resistance. Electric current. In previous chapter, chapter number 11, we discussed the behavior of charges at rest. We discussed electrostatics. Electrostatic means charges at rest. We discussed the force of interaction between charges, electric field of charges. In short, we discussed stationary charges in electrostatics. But in this chapter, current electricity, we will discuss moving charges, behavior of moving charges. Electric current. The movement of charge from one point to another point with respect to time is called as electric current. Moving charges shows another behavior, and we will discuss this in this chapter. According to the definition of electric current, the electric current is defined as the charge flowing through any section of the conductor in 1 second. Formula of current is I is equals to Q divided by T. Here Q represent charge and T represent time and I represent current. I is equals to Q upon T if the rate of flow of charge is steady. It means that equal amount of charges are flowing in equal interval of time. And I is equals to dq divided by dt if the rate of flow of charge varies with time. It means that if there is variation in flow of charges with respect to time, so we call it variable current. There are different types of current: steady current, varying current, and alternating current. Let's discuss its types by the help of graph. Here, vertical line on y-axis represents current and horizontal line along x-axis represent time. Straight line, which is represented by A, shows that current is not changing with time. With respect to time, current is constant. So we can say that steady current, which does not vary with time, is represented by this straight line A. Now you can see that line B originates with origin is a straight line but along z-axis. It shows that amount of current is changing with respect to time, and similarly in graph C you can see that amount of current is changing with respect to time. So graph B and C represent varying current whose magnitude varies with time. Graph D represents that magnitude of current as well as direction is changing with respect to time. Here in graph D we have positive and negative pulses of current, and this graph defines alternating current. Alternating current whose magnitude varies continuously and direction changes periodically. In alternating current with respect to time, magnitude and direction of current continuously changes. That's why it is called alternating current, because we get positive and negative pulses with respect to time. Electric current is divided into two types: conventional current and electronic current. Conventional current is a type of current in which we say that charges move from positive terminal of the battery towards the negative terminal of the battery. This type of current is not practically present in our circuits, but for our convenience, we say that this current is due to the electric field, because we have discussed in chapter number 11 electrostatics that direction of electric field is always from positive charges towards the negative charges. Here in this figure you can see that charges are flowing from positive terminal of the battery towards the negative terminal of the battery. According to the definition, conventional current is the current whose direction is along the direction of the motion of positive charge under the action of electric field. Electronic current is practically present in our circuits, and it is defined as the type of current in which charges move from negative terminal of the battery towards the positive terminal of the battery. Here in this figure you can see that electrons are flowing from negative terminal of the battery towards the positive terminal of the battery, and the motion of these electrons is against the field. According to the definition of electronic current is due to motion of electrons in the direction opposite to the direction of electric field. Drift velocity in a conductor. According to the definition, drift velocity is defined as the velocity with which the free electrons get drifted towards the positive terminal under the effect of the applied electric field. We know that conductor is a metal, and in a conductor there are many free electrons, and these free electrons move randomly within a conductor and collide with each other. Due to the collision with each other, these electrons move randomly in different directions, because due to the motion and collision, the direction of motion changes. Because in a conductor, electrons move in random direction, so there is no net flow of charges in any particular direction. Hence, we do not get any current due to this random motion of electrons within a conductor. But when we apply electric field, electrons get drifted towards the positive terminal. As in this figure, you can see that we have taken a conductor and it's connected with battery. Before applying voltage, electrons were randomly moving, and due to their motion, net current was zero. But when we provide potential difference, electrons start moving towards the positive terminal of the battery, because the electrons experience a force in a direction opposite to the electric field. We know that electric field is from positive terminal of the battery towards the negative terminal of the battery. So because electrons are moving and force is applied on these electrons, so these electrons move with drift velocity represented by Vd. Drift velocity is defined as the average velocity with which free electrons get drifted in a metallic conductor under the influence of electric field is called drift velocity. The drift velocity of free electrons is of the order of exponent minus 5 meter per second. Current is directly proportional to drift velocity. Electroencephalogram EEG. Electroencephalogram or EEG is a neurological test that uses an electronic monitoring device to measure and record electrical activity in the brain. As there are large number of neurons in our brain and they have ionic current in our brain. So by using EEG, we can measure the electrical activity in the brain. Special sensor electrodes are used to measure this electrical activity in the brain. These special sensor electrodes can measure voltage fluctuations in brain through ionic current of neurons. Electrodes measure voltage differences at the scalp in the microvolt range. Voltage traces are recorded with millisecond resolution has great advantage. Brain neurons mostly consist of sodium, potassium, calcium, and chlorine ions. Due to movement of these ions in brain, electronic current is generated. This electronic current is also known as brain current. Recorded result will be in wavy lines, and these graphs can be analyzed, and from the result we can find the behavior of brain. These images show the EEG. You can see that electrodes are attached to the scalp for recording the electrical behavior of neurons in the brain. From the result we get graph. Here we have few EEG potential graphs that are indicating the state of brain. For excited state of brain we have this type of graph. For relaxed state we have this graph. For drowsy state we have this graph. For asleep state of mind we have this graph. For deep sleep of brain we have this graph. When a person is in coma we have this graph. Ohm's law. Ohm's law gives the relation between applied potential and current flowing through a circuit. Statement of Ohm's law is the electric current flowing through a conductor is directly proportional to the potential difference across the two ends of conductor when physical conditions such as temperature, mechanical strain, etc. remain the same. Mathematically, we have direct relation between current and voltage. I is directly proportional to V. Here constant of proportionality is R, resistance. Graph between applied voltage and current is a straight line because there is a direct relation between voltage and current. When we increase the voltage, current increases. As we have already discussed in drift velocity, that by increasing voltage, drift velocity increases, and due to increase in drift velocity, current also increases. Those conductors which obey Ohm's law are known as ohmic conductors, and those which do not obey Ohm's law are known as non-ohmic conductors. Normally we have non-ohmic conductors because when current flow through a conductor, the temperature of conductor increases due to the flow of current. Due to increase in temperature, resistance varies and we get a non-ohmic curve in this graph. This graph shows that a given change of V causes a correspondingly smaller change in I at larger values of V. Hence, slope decreases with the increase of voltage. Electrical resistance. Basically, when current flows through a conductor, its flow is opposed by the conductor, and this opposition to flow of current is electrical resistance. According to the definition, the resistance of conductor is the opposition offered by the conductor to the flow of electric current through it. From Ohm's law, we know that V is equals to IR, and by rearranging, we get R is equals to V upon I. From the figure, you can see that this hand is opposing the flow of current. This hand basically represents the resistance of current. Resistance depends upon a few parameters. Resistance is directly proportional to the length of the conductor. R is directly proportional to L. When we increase the length of the conductor, resistance also increases. Larger length means there is possibility of more head-on collision of electrons in the conductor, and due to this collision electrons lose their energy which was provided by the voltage. So by increasing length of the conductor, resistance also increases. Resistance is inversely proportional to the area of conductor. By increasing the cross-sectional area of the conductor, electrons get more space to flow and resistance is decreased. Resistance is directly proportional to the nature of material. For conductors, resistance increases with increase in temperature, because with increase in temperature free electrons moves fastly and they collide with each other, and due to collision their resistance increases. For semiconductors, with increase in temperature resistance decreases because electrons get more energy to jump from valence band to conduction band. In insulators there is high resistance to flow of current. By combining the above relations at constant temperature, we get R is directly proportional to L upon A. Here constant of proportionality is equals to rho. Rho is constant of proportionality and known as resistivity or specific resistance of the material. We will discuss resistivity in next lecture in detail.